Well, welcome everybody. Thanks for joining us for this another in a quarterly series of seminars on soil moisture hosted by the National Coordinated Soil Moisture Monitoring Network. My name is Marina Skumanich. I'm a staffer at NIDIS, but on duty to the National Coordinated Soil Moisture Monitoring Network. So very happy to have you all here. So today we're going to be focusing on soil moisture and wildfire, and specifically the opportunities to improve fire danger rating systems around the country and actually internationally as well. There are few fire danger rating systems that currently utilize soil moisture, yet there's a growing body of evidence of the value and benefits soil moisture can bring to those rating systems. So we're going to have a couple presentations today just to give you a little bit more information about that. Very briefly, National Coordinated Soil Moisture Monitoring Network. Again, I imagine most of you have seen this slide. This is just a statement of our purpose, which is to provide a coordinated, high-quality, nationwide soil moisture information system for the public good, drawing on the three streams of data: in situ, satellite, and model data. And we do that through two complementary activities: building up this network of data networks across the country with in situ, as well as, again, the other data streams. And then also complementarily building up a network of people so that we can have sharing on new research and opportunities there. So soil moisture and wildfire today, improving danger rating systems. Again, we'll be reviewing the opportunities for applying soil moisture to those systems, starting with a presentation by Dr. Tyson Oxtener on the sort of giving an overview of research of the opportunities with soil moisture and how we can benefit wildfire, risk assessment, et cetera. And then we'll shift to a specific opportunity example of that, which is the TopoFire model, high resolution daily gridded soil moisture model, which we are seeing as a good, clear opportunity to help inform the US fire danger rating system. So I think with that, I'm going to let each of them introduce themselves a little bit more, and I'm going to change presenter to Tyson.
Okay, thank you, Marina.
So you should see that invite.
Yes.
Oh, and before you start, Tyson, let me mention to folks, if you're not as familiar with this platform, we don't really have an open chat system, but we do have a question box, question panel, where if you have questions going along through the presentation, put them in there, and then they get queued up, and I'll bring them up with the presenters after their presentations. So go ahead, Tyson.
Okay, thank you so much, Marina. Thanks for everyone signing on today. Thanks to NIDIS and the National Coordinated Soil Moisture Monitoring Network for the opportunity to talk with you all today about how we might use soil moisture information to better understand and predict wildfire danger. And if I can, yeah. So we've been working on this as an interdisciplinary team, including the folks shown on the screen here and others. I want to particularly highlight Eric Kruger, who is a research associate in my group and who has led a lot of this work from our side. And then also recently had a grant from the South Central Climate Adaptation Science Center with my colleague Matthew Levi from the University of Georgia. And through that grant, we had a series of workshops and were able to start working with all of the other folks you see listed here on a review article, which is just being published any day now in the International Journal of Wildland Fire. And so if these slides are available later, you should be able to click on the link and you can kind of follow that paper. It should be in its full version online, I would expect within the next couple of weeks. And so it's been great to work with these folks from across the nation and a colleague in Canada as we address these issues around soil moisture and wildfire. You'll be hearing from Zach Holden here in just a few minutes. So our motivating question has been, how can we use these soil moisture data that are increasingly available to better manage the impacts of fire on people and ecosystems? And as most of you are probably aware, those impacts are not all negative. There are certainly positive impacts of fire, and there can be negative impacts, and we want to try to manage fire in a beneficial way for communities and natural ecosystems. And it's been about a decade for me. It's really a journey of discovery, a very interesting one for me, is coming from a soil science background where this was not a topic I was familiar with when we began. But we started working on this about 2011, 12 sort of time frame. And one of the first things we learned, we published here in this paper by Kruger et al. 2015, showing that soil moisture strongly affected the size of growing season wildfires here in the southern Great Plains where we're located. And so we started to follow that chain, and we then started to explore the possibility of using soil moisture information to estimate wildfire probability. And so we found that there were different relationships between soil moisture and wildfire in the growing season and in the dormant season, and we could account for those with these probabilistic models of fire danger, particularly for large fires. As we started to work on this, people began to talk with us about KBDI, Keach Byram Drought Index, which is a very important fire danger indicator in many places, widely used for this purpose. And so we needed to compare soil moisture observations with KBDI. And at least in our context, we found that soil moisture measurements provided better growing season wildfire predictions than the KBDI drought index. We just wanted to understand the mechanisms of that, and so we started to get out in the field and collect measurements of the vegetation and the fuels, and started to try to understand mechanistically what's happening. And we could see that the fuel moisture in our grasslands and the curing of those fuels, so that's the process going from live to dead fuels, were both strongly linked to the soil moisture conditions. And continuing that line, we were also able to show that if we have soil moisture observations, we can use those to get better predictions of grassland fuel loads. And so I'll just show you some highlights of this journey from these manuscripts, kind of in reverse order here. So starting with this last one about fuel loads. And again, focused here on grasslands, but as the presentation moves forward, we're going to cover a lot of other land cover types. So if you're not a grassland person, that's okay. We're going to get beyond that. But we wanted to model these herbaceous fuel loads, and we did that starting with a pretty simple and widely used modeling approach that starts with modeling evapotranspiration using the FAO 56 approach. Some of you may know that. It's a very widely used approach, and it's represented by this relatively simple equation shown here. And we're basically scaling the reference ET, which comes from weather data. We need to know something about the vegetation types, and that's represented in this KCB. That's basically a vegetation parameter, represents the density and phenology of the vegetation. And then we have a water stress coefficient that affects the plant transpiration. We also have water availability impacting evaporation from the soil. And those are the KS and the KE coefficients here. And to get those, we need to run a simulated water balance on a daily time step. Once we have done that, then we can peel out this KCB part. This is the part that lets us estimate transpiration by the vegetation, whatever vegetation we may have on the site. And once we've estimated the transpiration, we know sort of from basic plant physiology that there tends to be a fairly linear relationship between the amount that a plant transpires and the amount of biomass that it produces. And so we can normalize the transpiration and then multiply it by a water productivity constant to estimate the biomass, which in our application would be the herbaceous fuel load. And so we calibrated this for a site that we have here near Stillwater. It's called the MOIST site. It's the Marina, Oklahoma In Situ Sensor Test Bed. We had a flux tower there measuring the ET. We had regular sampling to measure the vegetation, biomass. So we were able to estimate these vegetation parameters shown here in green and the water productivity here in the lower equation. So then we were able to run this whole framework, if just modeling as shown here, but also we asked the question, well, what if we don't have to run a water balance model, but we can simply insert our observed soil moisture data every day? So we ran the model with and without this direct data insertion to see the results. And then we thought, you know, what the heck, we calibrated this on one site, let's just apply this across the whole state. So we picked 25 counties across the state of Oklahoma where we could get some good data on the grassland productivity across 3 different years, and we could see what we could predict. And so just right to the results here, here's our predictions on the x-axis, which is shown as a modeled hay yield. You can just think of this as a fuel load. And on the y-axis, we have what was actually measured. And so we're doing okay. We're probably a little bit low in terms of what we're predicting. The observations were a little bit higher than our predictions, but generally our correlation was pretty good. Our Nash Sutcliffe efficiency was 0.55. That's not so bad. And it was across a pretty wide climate range here spanning the state of Oklahoma. This is with the insertion of the soil moisture data. If we don't insert the soil moisture data, we just run the water balance and the model apart from observations, then our Nash Sutcliffe efficiency drops to 0.1. So we're seeing a clear benefit towards inserting the soil moisture observations to predict these herbaceous fuel loads. And this would kind of be a first step towards maybe a larger scale system to do that. So that's what we've done on fuel loads. This slide is really dense. Represents a tremendous amount of effort to gather these data. So I'll explain what we have here. There's 2 years of data. The left-hand column is 2012. The right-hand column is 2013. The top panels show the fraction of available water capacity, or FAW. So this is the soil water storage normalized between the upper limit or field capacity, which would be 1, and the lower limit or the permanent wilting point, which would be 0. So we normalize the soil moisture data in terms of FAW. And you can see how it varies over time. These months, if you can't see them, are May through November of 2012, and then the same months in 2013. So in 2012, you can see the FAW was declining, the soil moisture was declining right up through the month of August. We had very severe drought in 2012, as many of you remember. 2013 was much wetter. This dashed line in 2012, August 3rd, is the day when we had a large wildfire outbreak quite close to our study site. And this happened when the fraction of available water was equal to 0.24. That fire burned about 35,000 hectares and destroyed, I think, over 100 homes. The remaining panels here are fuel moisture panels. And so the second row of panels are the green fuel moisture. You can see that it was declining along with the FAW during that drought event. And the third row of panels is the mixed fuel moisture. And you can see those again also declining and reaching minimums coincident with the occurrence of that wildfire outbreak. And so here we're starting to kind of see how the soil moisture and the vegetation or fuel moisture are linked. 2013, there were no large fires, and the soil moisture, vegetation moisture, fuel moistures were all much higher. Except for right at the end in late 2013, we did have a sharp decline in both the soil moisture and the mixed fuel moisture. In these grasslands, we haven't seen much evidence of any correlation between the soil moisture and the dead fuel moisture, which is almost always quite low in these grasslands. Okay, so that's what we're learning about fuel moisture. If we break those data out and look at the relationships more directly, this plot shows the relationship between soil moisture or FAW on the x-axis and mixed fuel moisture. So this is if you sample the entire fuel bed in the grassland and its fuel moisture values. So once we drop below some critical level, which seems to be around FAW of about 0.6 roughly, then we see a strong linear relationship between the soil moisture and the mixed fuel moisture during the growing season. As FAW continues to decline, if we drop down into the level of FAW values below 0.3, then we see this inverse relationship between the curing rate and the soil moisture. Now remember, the curing rate is the rate at which live herbaceous fuels are being transferred to dead fuels. And this is really interesting to me. We actually, curing rate is not a parameter, to my knowledge, in any of our fire danger rating systems. We just approximate a curing level, but it's really a dynamic process, and this suggests we might be able to use soil moisture conditions as one of the predictors for these dynamic curing rates. The maximum rate reached up around 13 grams per meter squared per day. That happened in September 2013 when the FAW was very low at 0.21. And just for some context, data from Australia shows that grassland dead fuel loads of 70 grams per square meter are sufficient to propagate fire. And so if you imagine here we're at 12, so about 5 or 6 days, 6 days at this level are going to give you enough accumulated fuel to support a wildfire. Okay, so now we can kind of summarize, and this is a synthesis figure that I think is really helpful, and so I'll unpack it a little bit. On the x-axis, again, we have FAW. Again, these are based on data from Oklahoma, but now not necessarily just grassland. Some of these data expand across all the land cover types in our state, including forests and shrublands. And so on the x-axis, we have the number of the left y-axis, we have the number of large wildfires. On the right y-axis, we have the probability of a large wildfire. And you can see how these change as a function of the soil moisture. And this is again for the growing season. So the probability of a wildfire is shown with the solid black line, and the number of large wildfires are the gray bars. So as FAW begins to decline, there's a threshold of about 0.6 where we've seen that fuel moisture begins to decline. If the FAW drops even lower, around 0.4, that's where we've seen evidence that the transpiration and growth begins to slow down. We have data, which I didn't show you earlier, but relating NDVI and soil moisture. So as we drop below a FAW of about 0.36, that's where we see the greenness of the vegetation begin to decline. And once we drop below 0.3, that's where we see the onset of rapid curing and the transfer of live herbaceous fuels to dead. Once we get down below 0.2, that's where we really see this elevated number of large wildfires occurring. So that's all kind of explained here in these bullets, these four different thresholds that we see highlighted here. So I think this is kind of what we're learning, at least holding across the ecosystems that we have here in Oklahoma. And so we have a growing body of research that's giving strong evidence that soil moisture is a key predictor of fire danger, and it's not yet effectively integrated into our fire danger rating systems. Now, if you are appropriately skeptical, you would say, yeah, but what about other regions? And so that's why we did the review paper, to see what others were finding in other regions. And so when we look at in situ soil moisture observations, those have been linked to live fuel moisture of shrublands in Italy going back to 2007. If we look at remotely sensed soil moisture, that's been linked to the extent of forest fires in Siberia, dating back to 2009. And if we look at modeled soil moisture values, those have been strongly associated with large wildfires in Florida going back to 2010. So over the last, 10 or 15 years, there's been a real emergence of these type of observations in different places around the world. Remotely sensed soil moisture can be used to estimate live fuel moisture across the U.S. A recent paper showing a predictive ability of around plus or minus 20%. And then particularly for those of you interested in forest, there's been a growing body of evidence showing that the dead fuel moisture is linked to the soil moisture, particularly in forest. And so we'll say a little bit more about that as I move to wrap up here. This figure on the right here is showing the red area are simulated areas of soil moisture stress and correspond with predictions of wildfire. And the black circles there show where the wildfires actually occurred. So some people are starting to take this. This is from the work of Waring and Nicholas Coops, and they're starting to take these concepts and apply them to large-scale modeling, including in our forested systems. Now, I want to say just another word about soil moisture and dead fuel moisture in forests. And as I mentioned, there's growing evidence from places around the world, California, Canada, Australia, China, Thailand, that are showing relationships similar to the one that I have on the screen here. This is from a recent study in the foothills of the Sierra Nevada. And so this is showing that when soil moisture is low, when the soil is relatively dry, it's not particularly well related to the dead fuel moisture. That's the y-axis here. But above some level, here it was 21% of soil moisture. Above that, there was a significant relationship between the soil moisture and the fuel moisture. And this kind of finding has been also replicated in Australia with controlled experiments where they did physically based modeling and field experiments, confirming that we have liquid and vapor flow between those litter layers and the underlying soil. And so these high soil moisture conditions can be a really important regulator on dead fuel moisture when it's on the ground and wildfire in forest. And so that's been really interesting for me to learn about. There's some unique challenges to working in forested environments because of the complex topography, limited access to get in there and observe what's happening. And we just have not that many or not enough in situ soil moisture monitoring stations that are directly under the forest canopy. We really need that. Unfortunately, the U.S. Forest Service weather station network, which is called RAWS, does not, most of those stations do not measure soil moisture, and it would be excellent if they did, and maybe that's coming. But the other challenge we have in forest is the limited ability for our satellites to penetrate those dense canopies and see what's happening on the forest floor. And so one way forward may be through some new modeling efforts. And so this is a diagram mostly to point you forward to Wildfire. So this is one of the outputs from the Wildfire system. And I'll be wrapping up with 2 more slides here and then hand it over to Zach to talk about the Wildfire system. So some key remaining questions that we have is, how to best represent soil moisture. Is it anomalies? Is it absolute values, fall, or something else? What are the most important soil depths? How do we use different sources of soil moisture information? And then what about organic soils? What about the duff layer, organic soils, peat, tundra, wetlands? What about these kind of soils and their link between burning of those organic materials and the soil moisture conditions? What about the impacts on prescribed fires? And probably most importantly, how can we engage wildfire professionals to begin to use this new research to make better fire danger predictions? So this is a really busy figure. It's a diagram of the U.S. National Fire Danger Rating System. And I'm just going to real quickly mention 5 areas where soil moisture data might be relevant based on our data. So it might be a useful replacement or complement to KBDI. That's one way. It might be useful to model fuel moisture for both live and dead fuels. It might be useful to predict curing of herbaceous fuels, and it might be useful to predict dynamic fuel loads, particularly again for the herbaceous fuels. So with that, thanks to all of our sponsors, and I'm going to pass this over to Zach to talk about Topo Fire.
Actually, Tyson, we're going to take one question for you that came up. Well, somebody's telling you did a terrific talk, but there is one question that's directly related to your presentation. I think maybe best to get right now, which is, do you think measurements of matrix potential would be more powerful in your analysis, or does FAW sufficiently points?
Okay, thank you for the question, and that's an excellent question, and I really don't know the answer. And so it's something that we should take a look at. We can estimate major potential from our sensors here in Oklahoma, and so we should do that analysis, and we haven't done it yet. So whoever asked the question, come and help us do that.
I'll share the name. There's actually another one that's is related to slide 8.
Okay, I don't know what slide number. Oh yeah, I do have slide numbers, sorry.
Okay. On slide 8, how should I think about your greatest discrepancy between either your WF probability right axis or your number of WF left axis and your FA, your minimum? Wildfire.
Yeah, so like the shapes don't quite match, maybe is what they're getting at. The curve doesn't exactly match the histogram, and that's a great observation. Those two were done as completely separate studies and were never combined until we made this figure for the review paper. So the curve comes from logistic regression, which forces an exponential kind of pattern onto the curve. And maybe exponential's not the best fit for this relationship. Maybe there's another form that would be more appropriate.
There was a follow-on question there. Have you or anyone looked at FA and fire severity?
No, that's a great, that would be a great thing to do also. Thank you for the idea. We have not done that, and I don't know of anyone who has.
Okay, so all the rest of you on this on this seminar, that's an opportunity for you as well. Okay, with that, let's switch over to Zach. Thanks for that.
Can you make that switch, Marina?
Should have just happened.
Okay, great.
Thanks.
Can you hear me okay, Marina?
Mm-hmm.
Okay. Hey, thanks, folks who are out there. I'm just talking to myself. I have no idea. What's up, Marina?
Want to go into slideshow mode? Slideshow.
Oh yeah, thanks. Can you see my screen all right?
Mm-hmm. Screen's great, and it's
okay.
Functional now. There we go.
All right. Well, hey, I'm going to talk pretty quickly here for about 15 minutes. This is kind of old/new work. I just want to give a shout out to Alan Warren and Alan Swanson. They did a lot of the heavy lifting for a lot of the work that I'll show today. You know, I work for the Forest Service. We grow trees, among other things. And so, you know, one of the big challenges that we face in managing our lands is complex topography, right? And particularly here in the Northern Rockies, you know, you get on a north-facing slope where we have, you know, less shortwave radiation. You get just tremendously different conditions, much higher fuel loads, different species composition. terrain here is everything. It's you know, what we plant, how fast it grows, how it'll burn. It's really important. I try to frame this, you know, and push this message to the fire community via the old fire triangle. If any of you have ever been through like one of our early fire trainings for like a red car training, they show you this little diagram, right? And we talk about this kind of interaction between weather, terrain, and fuels. Well, the intersection of all those components is what we think of as topoclimate or microclimate, right? It's really the kind of finer scale patterns that result as an interaction between those things. So we had support from NASA starting back in 2012, 2013, basically to try to develop a terrain resolved wildland fire assessment system for the US. And the principal goal of that was to incorporate snowmelt timing into our fire danger assessments. So I'm going to share just a kind of an overview of that work here. Through that project, we developed basically some high resolution daily gridded data sets, so 250 meter spatial resolution. We do that for this historical period starting in 1979 up through just about present. And then we generate these grids, you know, for temperature, humidity, and shortwave radiation every day with about a 1 day lag. You know, the spatial resolution here is really critical. That 250 meters, although it's expensive to kind of manage and generate, it allows us to resolve, you know, some of the finer scale features of terrain that we're interested in. And in particular, you know, it's all about solar radiation, where south-facing slopes get a lot more incoming shortwave radiation than, say, a corresponding north-facing slope. So we have daily, you know, daily cloud and shade corrected radiation data. And starting in probably about 2010, I was just out of graduate school and I really wanted to try to understand fine scale variations in temperature. We put out massive networks of little $20 temperature and humidity sensors all across the Northern Rockies. We had some in Oregon and Washington and Canada as well. And we used those to essentially to develop correction factors for downscaling. So we use those. I don't have time to go into the methods here, but if you're interested, you can track down this paper where we talk about how we kind of use those data and blend them with reanalysis data sets to, you know, to develop basically temperature grids that have adjustments for aspect position and cold air drainage and the like. So we feed all of those daily weather grids into a really simple soil moisture model. Funnily enough, this model was really developed just as a covariate for modeling maximum temperature. One of the things that we learned from our sensor networks is that, you know, soil moisture and solar radiation interact to determine kind of how warm a particular slope facet gets. So our south-facing slopes, as they dry down, they get a lot of incoming shortwave radiation, get a lot warmer than our north-facing slopes that are a little bit wetter and get less radiation. So this was really a throwaway model. It's just a single layer bucket model. You know, new precip or melting snow kind of fills the bucket. Anything in excess of storage goes to runoff. You have a simple, you know, evapotranspiration that governs the basically moisture loss from the soil. But, you know, we have, you know, a uniform bed of vegetation. This is just a, you know, grass model. There's no lateral flow of water, no bedrock leakage. It's just a really, you know, just a really basic model. The water holding capacity in, you know, the size of our bucket essentially is defined by a water holding capacity grid. This was developed a long time ago using Sergo data, but modeled and infilled with StatsGo and some other variables to fill in the missing gaps. And, you know, on top of the soil moisture model, we did spend quite a bit of time developing a snow model to run on top of, you know, on top of the soil moisture model. So we took a model from SWAT, calibrated it using a bunch of SNOTEL stations, and modified the model a little bit by calibrating it with incoming radiation rather than just a latitude factor, which is what that model originally used. Here's some validation results at all of our SNOTEL stations. This is for SWE. We're not doing too bad, I would say, for, you know, a model that's running across the whole West. We actually calibrated the model to snow off days, to snow free days. And we did this really with fire in mind, where we want to understand when fuels begin to cure. So we can, we can model across all of these sites snow ablation date with, 9 to 10 days of error on average. What that gets us, again, what we were really after is a model that we can impose on top of fuel moisture models that would resolve the huge delay that we see in snowmelt timing on north-facing slopes. And you'll see at higher elevations here in the northern Rockies, north slope, the snow will melt off as much as a month later than a corresponding south slope at the same elevation. And we know that's got to be important for fire behavior, fire spread, that kind of thing. So that's, that was our goal. And again, just kind of pointing to some of the outputs here. This is the climatic water deficit. This is a component of that soil moisture model. We use this in ecology quite a bit, right? And even in fire a little bit. This is the unmet atmospheric demand for water. And what we want to highlight here is just that, again, that our north-facing and south-facing slopes have very different water availability. We're capturing some of the dryness on those south-facing slopes. Again, if you look at SWE here in this panel, you'll see that there's a substantial delay in snow melt and more snow accumulation on the north-facing slope. And in this final panel down here, we're looking at the energy release component. That all of that results in a really different kind of characterization of the fuel moistures on north and south-facing slopes. So we've gone to a lot of trouble to try to resolve some of these terrain variations. Recently, some colleagues of mine, Zach Hoylman, Kelsey Jenkso, have been doing some work with these data sets, and we started just by comparing them with the actual soil moisture data with soil moisture observations. So they assembled all the SNOTEL stations, any mesonet that would share their data, a bunch of soil moisture observations, and then they compared some different soil moisture models with the observed soil moisture at all of these stations. And what we found, kind of surprisingly, is that this TopoFire soil moisture model does a pretty good job. This is across 600 some stations, thousands and thousands of days. Pearson's R of 0.7 really isn't too bad when you consider just the incredible variation on the landscape out there at these different sites. And they ended up doing a little bit broader comparison with some other available soil moisture data sets. So from SMAP, SMOPS, CFSV, CPC, soil moisture. Some of these I actually don't know or haven't worked with. But what they found is that this TopoFire soil moisture data set actually does quite a bit better than these other soil moisture data sets. So, that has us, I guess, kind of encouraged that we can use, this model or these data for, sort of more applications for fire and drought management, et cetera. Here's just a kind of a little movie that Zach Hoylman made of 2022. This just lets you see kind of the evolution of soil moisture, where we start kind of dry in the southwest, and then you can kind of see the monsoon come in, and that classic dipole, or the northwest begins to dry out. If you want to see the kind of current maps of soil moisture, we're kind of reviving the web front end, and this is the current location of it if you want to check it out. And then the daily data sets, if you want to actually download those historical soil moisture grids, you can pull them down here. I encourage you to be a little careful. It's probably 5 or 6 terabytes of data, so it's kind of big, but they are available if you want to look at them. And then finally, just kind of a nod towards next steps. What we plan to do with this data now, working with Matt Jolly at the Fire Lab, is to basically redesign the Keach-Byram drought index. And it's an old model that's still really widely used in fire management, but it's very, very primitive. We know we can improve it. And through that work, we'll do an analysis of kind of historical wildfire activity and soil moisture relationships. I just have kind of one quick result here from our KBDI. We have kind of re-engineered that Keach-Byram drought index using our model, put it on the same scale as the original KBDI, and then we fed it through here Fire Family Plus, which has logistic regression models that predict basically large fire occurrence. And so here's just a comparison of the old KBDI versus the KBDI reformulated with our soil moisture model. And you can see we're doing them, a little bit better, as you'd expect. So we'll expand this analysis now across the whole US and see what it shows. And then I guess finally, I just want to kind of point to where we're going. We've spent the last couple of years now working with a much more sophisticated energy balance model called ECHO. And, this is, I feel like where all of us understand we need to be going. We need to be really using, more detailed, sophisticated multi-layer soil moisture models in concert with observations to map soil moisture dynamics. And I'll just show kind of one result from our work with ECHO, where we've calibrated it at the SNOTEL stations and can now point it to any location and get a pretty nice soil moisture SWE trace, for pretty much anywhere in the West at this point. So I guess stay tuned on that. We're getting ready to publish some of that work here shortly. That's all I've got. Marina, I'd be happy to answer any questions.
One thing I'm going to ask you, Zach, is if you could explain how the TopoFire work and the adjusted KBDI, which I think we were considering calling KBDI ET, just to sort of highlight the fact that it was bringing in some of the soil moisture and other ET dynamics, how that's going to fold into the fire danger rating system, because that's part of our effort as well. And I think you can speak to that better than I can.
Sure. Yeah. So Matt Jolly still maintains a lot of the National Fire Danger Rating System. Tyson showed a figure of kind of how he'd redesigned the NFDRS. They still use in the Fire Danger Rating System in the U.S. the Keats Byram Drought Index. So it's actually a fairly trivial thing to swap it in there. I think once we're done and we've recoded it in something besides R, either Python or C++, it'll be fairly straightforward for Matt to transition that into, in place of the old KBDI. So.
Well, I think the larger story, it will be straightforward technically, but then we do also have the need to ensure that the users are comfortable with the change. And then I'm not sure what kind of calibration would be needed, or if that would just be actually transparent to the users.
My suspicion, Marina, is that just using standardized anomalies of soil moisture will be more predictive than the KBDI, but there's such a history with that index, including its range, its scale from 0 to 100 or 0 to 800, that I think there's value in keeping it in that range, and kind of keeping it in the context of the old index. But I think it'll be easy for folks to adopt once it's there.
Okay, that's good to hear. And it's also good to hear what you just said, which means next generation. We'll start with the KBDI ET, and then we'll move on to the real stuff. Soil moisture straight, like a straight shot of soil moisture. I do have one question for you, Zach. So from a colleague, I guess he's saying we've got to grab a beer sometime. That I probably wasn't for public consumption, but he did want to ask. Picture 1 cubic foot of snow. How should I think about how much of that volume sublimates versus melts?
Yeah, you're already getting like further into the details than any of these models go. So we have no sublimation term in that snow model. No canopy interception. I mean, we could go on, I think, for quite a while about what's not in it. And I think we just have to recognize that running things nationally at this resolution, there's limits to some of the details that we can build in to these models without just ultimately going to like a full physics-based energy model that has all of the kind of bells and whistles in it, right? But
yeah, well, it's always good to get these things on the list. I think several of you who have raised interesting potential areas of research here. I just also want to share, and I'm going to not be as educated about maybe some of you of this, but I was just speaking with a researcher down at UCSD about some testing she's done, showing that just even a simple linear reduction of soil moisture levels gives as good fidelity in terms of predicting impacts on wildfire as multi-layered, physically assessed fancy models. So just not to be glib about it, but just making the point, I think a little bit of where you were going, Zach, is that we have to balance absolutely getting the whole story with what delivers value, and sort of recognize the different places we'll get value out of less sophisticated models. That leaky bucket may still have a role going forward.
Agreed. Yeah, thanks, Marina.
Yeah. Okay. So anybody else with any questions? We've got I got just a few that I've asked, but again, if you've got any questions for either our presenters, please put them in the chat. Oh, sorry, not the chat, the questions box. But I'm going to invite Tyson to come back on. And while we're seeing if anyone else has questions, just want to ask both of you. I know you did both allude to some next steps, but maybe just to focus it in for each of you, Tyson and then Zach, what is your next step to move this forward?
That's a great question, Marina. Probably one I need to wrestle with. So I have, we've begun our soil moisture observations in forests just over the last few years here. So we are, monitoring deciduous forest site. We're monitoring a pine plantation site. And based on what, we've seen in the literature from other locations, I think I'd like to get into a better understanding of that interplay between the dead fuel moisture in these forested systems and the soil moisture of the underlying soil. And so that's potentially a next step for us. Also, maybe along with that at a much larger scale, interested to pursue some of these modeling angles like Zach has mentioned, whether that's TopoFire or some of the other candidate models out there to see, where do we find that balance between realism and functionality that helps us to make a difference for these applications like fire danger rating, but also drought monitoring and other important applications that we're working on.
Right. Yeah. Just to mention, maybe Zach would be adding this too, but it's interesting to me. It's worth saying that the Forest Service is really interested in soil moisture for management questions, separate from fire. From simply, is this the time to harvest? Can we put the and actually, we've been heard about the value of monitoring like hurricane impacts in southern U.S. and what that means for forest, water, soil moisture. And Zach, how about you? Next, you may have echoed that. Maybe echo is your next focus. Go ahead.
My little sort of pet thing right now, I guess the most important thing I see that we're missing in sort of fire danger, fire behavior, fire severity, sort of anything wildfire related is the plant hydraulics, basically how stressed the trees get. We all know soil moisture is important, and when the soil gets dry, things get dry. But I think we're missing a link between soil moisture and what the trees do in response to basically not having water available, and then when fire comes, how it spreads through that canopy. And I feel like capturing that plant hydraulics is going to be really critical. So with that echo model that I mentioned briefly, Marco Moneta had programmed into that a plant hydraulics module that actually couples the soil moisture, vapor pressure deficit to predict the leaf water potential, so how much tension there is in the stem of the trees. If we can take something like that and map it with any kind of reasonable accuracy, I think it's going to be eventually profoundly important for how we manage fires. But anyway, that's my kind of dream project right now.
Right.
Yeah, we could link that back to the questioner earlier who asked about should we instead be monitoring the soil matrix potential, which in some ways links more naturally with the kind of plant hydraulic models that Zach is mentioning there.
Okay. Any more questions? Really exciting stuff. I know that you guys have this review paper coming out any day. Well, I guess it's kind of out, but anyway, publicly available any day.
Just the abstract so far. They haven't put the whole thing online yet.
Okay. So, and you may have mentioned this to me already, but I just thought to share with the audience, do you elucidate a little bit in that paper, sort of the different paths, thinking about soil moisture impacts on grasslands versus forests? I mean, you did speak to that a little bit in your presentation, Tyson, but you know, I just feel like that's just such an important matrix to get started.
Yeah, it is, and then I would just say that we have a lot to learn about that. Those differences across different vegetation types and soil types. So we can go to the forests of the West. We can look at fires in the Arctic. We can look at the wetlands in Florida or North Carolina. And there's evidence for all of these, fire behavior in all of these systems being impacted by soil moisture. But the mechanisms and the relationships are likely to differ in some important ways across those. And we've shown, you know, I think we were understanding some pieces of those differences, but we're probably just scratching the surface of that.
Right. So that if you're looking to early warning, you're going to have to be looking at a different time period or different kinds of antecedent conditions, et cetera.
Probably so.
Yeah. Okay. Well, any more questions from the audience? Any final takeaways either of you want to leave us with?
Thanks, Marina, and thanks, Zach, for your contributions today. I really enjoyed it.
Yeah, no,
Thanks, everybody.
It's been a great presentation, really important. And just so folks know, you probably would imagine this, but this relationship between soil moisture and wildfire risk is a priority of the NCSFMN. We do want to make sure we're harnessing this information to improve our ability to respond, and more than respond, have early warning for fire risks. Yeah, okay. Well, thank you very much, everybody. We're just going to give you a few minutes back to your day, and I really appreciate you doing this. And thank you so much, Zach and Tyson, for your presentations.
Okay, thanks, everybody. Thanks, Marina.
Bye, everyone. Yeah.
Bye.